Hello everyone, free radical part 6. So here also we will discuss reactions of free radicals. So let's have a quick brush up. Three fates of radicals. We have already seen this slide in the previous video. So the first type we have already discussed, under which we have seen pinnacle reaction, magmatic coupling and SL1 reaction, though this type is exceptional. So here what happens, two radicals, and mostly two radicals are same. So in these cases we have seen that. So when it is same, you can call it dimerization. So two radicals combining together and we are getting a spin paired molecule. So as if we have two R dot and they are connecting together and we are getting RR. So this part we have finished. Now the second one, which is the most common, and there are varieties types of reactions under this heading. So here we have radical and we have spin paired molecule, suppose AB, and here we will get a new radical, new spin paired molecule. So if this R dot is connecting with A, then we are getting RA and the new radical is B dot. So this will be the most common. So in today's video also we will discuss some of this, though it will take more videos to finish completely. And the last one, it is also always there is expulsion of a small stable molecule such as CO2, CO or N2. So in this case, from a single radical, as you can see here, PHCOO dot, we are getting new radical and spin paired molecule. But the most common is this one, most common and most important. So today we will see this one, the second one. So under this, the first we will see addition of radicals to multiple bonds, and mostly the examples that we are going to see, it is CC double bond. Now these radicals, it may be carbon radical or it may be some other radicals. Okay. So 2 points we have to remember, that is the difference with ionic reaction. So in ionic reaction, when we have some reactive intermediate, there is some chance of rearrangement. But in this case, when we are talking about radical chemistry, it is to some extent different, and it has some advantages, because those type of rearrangement or elimination reactions are rare in this case. And another point is, it is often possible to bring about addition reaction, because we are talking about radicals addition to multiple bonds. So this addition reaction we can do without the protection. So we don't have to protect any group or deprotect any group, because these radicals are so selectively reacting with the multiple bonds only. So these are some points that we have to keep in mind when we are comparing with ionic reactions, where we have reactive intermediate, mostly C+, that is carbocation. So under this addition of radicals to multiple bonds, first we will see HBr addition to multiple bonds. Now if we do not have this, that is peroxide, then it will be simply addition of HBr to this CC multiple bond, and that is mostly according to Markovnikov. But when we have HBr, it is anti-Markovnikov, and I have selectively taken HBr because this anti-Markovnikov addition, it is observed only for this, and why it is not observed for other HX, that is HCl, HF, HI. For that you can check another video which I have done on this, and for that you can click on the link appearing on the screen right top corner. Okay, so this reaction we have here CC double bond and HBr in presence of peroxide. Now this reaction, if we go into the details of mechanism, first there is initiation, and remember we are discussing under the heading where one radical, it will react with some spin paired molecule, we will get new radical. Now this type of reaction you can also call it chain reaction, because from one radical you are getting another radical. So in initiation, this peroxide, either you use light or photo, so that is heat or light, there is this OO cleavage and we are getting RO dot. Now this RO dot, in presence of this HBr, it is capturing this HBr, it is capturing the hydrogen, and we are getting Br dot radical. Now the propagation step will start. So in this propagation step, now this CC multiple bond, it will be attacked by this Br dot, and it will be attacked in such a way that the Br dot, it is attaching to this terminal CH2, so that we are getting the radical which is more stable. The other possibility, if you consider, then the radical, it is at the terminal position which is less stable. So that is why this radical will be formed. And after that, now take this radical again in the second step. This radical will take a proton from another HBr molecule, and finally there is one more Br dot which can again start this first step of the propagation. So in this way we are getting this final product which we have already mentioned in this. That is a net reaction if you consider it is in this box, and this is the mechanism. Now obviously there is a termination, but we are not focusing on that elaborately, because termination steps, it can be combination of any free radicals in all possible ways. So it may be that two Br dot are connecting together, or any other two radicals are connecting together, but that is not important here. Important point is this, how we are getting this final product. Okay. Next we will see addition of carbon radical to multiple bonds. Now when it is carbon radical is adding to multiple bonds, CC multiple bond, obviously we will get carbon-carbon, new carbon-carbon bond will be formed. So here we can see we have Ri, this R may be any alkyl group, and we have CC double bond with a substituent Cn. Now AIBN we have taken full structure, it is already shown in the previous videos, and we have also taken this molecule Bu3SNH. Now this molecule, why it is taken? Now when we will see the mechanism, it will be clear. So here what is the net reaction? The net reaction, as you can see here, this R group is added to this CC bond, and which carbon it is added? The carbon which is not substituted. Okay, some more examples we will see, and after we have seen 3 to 4 examples, then we will see the mechanism for one particular reaction among these examples. So the next reaction, here we have BrCCl3. So here this CCl3, it is added to this position. Okay, so carbon radical that will be generated here is CCl3 dot. So this CCl3 that will be added to this position, and the Br that will be added to the other position. Now okay, so let me tell you, in this reaction we do not need any of these reagents. Okay, now the next one, here we have this alcohol, and this is obviously the CC multiple bond with C6H13 group. Now in this case, in presence of peroxide, here the radical that will be generated, that is clear from this final product. So the radicals that will be generated, if you consider this CH bond, if you break this, the radicals that will be generated, it is like this. And this is the carbon radical which will be added to the CC bond. So this is the newly generated bond. Okay, and see again it is added to that carbon which is not substituted. Fine. Here we have used a peroxide. Now this alcohol, if you modify it to this type of ester in presence of this reagents combination, then in presence of AIBN and Bu3SNH, now we are getting a different types of radicals. So when the alcohol is converted to this ester, we are getting a different type of carbon radical where this carbon oxygen bond is broken. Try to understand the previous one. This is the carbon radical through which the reaction is occurring, but in the next case, when we have converted this OH group to OCS SME group, now the carbon radical that we are getting, it is different. And again it is added to that carbon where there is no substitution. So we can say that addition of alkyl radicals to monosubstituted alkenes, it is taking place predominantly at the unsubstituted carbon of the CC double bond, which is clear from all of these examples. And these alkyl radicals that we are using here, that is added here, that can be generated in a number of ways, which we can see here. Sometimes we are using peroxide, sometimes we are using AIBN Bu3SNH combination. So whenever there is Bu3SNH, it is always associated with AIBN. AIBN is basically the promoter, which is when we see the mechanism, it will be clear. So Bu3SNH, it is taken in 1 or 1.2 equivalent, and AIBN, it is 0.05 equivalent is enough. Okay. Now, peroxide is required in those cases where we have to break bond which is more strong. But Bu3SNH AIBN combination, it can be used for in those cases where no such strong bonds we have to break. Okay. Now we have chosen this reaction. See, it is the first reaction. This one is chosen. Now this, for this reaction we will see what is the mechanism. So for initiation, this AIBN molecule, as you can see here, first there will be generation of this radical, same radicals 2 and stable molecule nitrogen is removed. This radical, ultimately it is taking the proton, that is SNH bond. Now this bond is very weak. This SN hydrogen bond can be easily broken. So here we do not need peroxide type of radical, which is obviously more reactive, which can break any hydrogen bond, hydrogen added to some atom, any type of bond can be broken by RO dot. But if very weak bond is we have to break, then this is sufficient. We don't have to use peroxide. So in this case, we are getting this radical which will now take part in the propagation step. So in propagation step, this Ri, where R is the alkyl group, this is the carbon radical generated, and Bu3SN, it is capturing this I from Ri, we are getting R dot. Now this R dot, that is the carbon radical, because we are now discussing addition of carbon radical to CC bond, okay, that is the heading. So this carbon radical now added to this carbon which is less that is not substituted, and ultimately this compound, this radical, it will take finally this proton from Bu3SNH, basically hydrogen atom, not proton. So that is why Bu3SNH, this reagent we have to use 1 or 1.2 equivalent, but AIBN is fine. It is just required to initiate this. Once this radical is generated, then the reaction will continue, because in the final stage you can see there is formation of Bu3SN dot. Okay. So this SNH, it is providing the final hydrogen which is added here, and we are getting this molecule RCH2 CH2SN. Fine. So this is the second type we have seen, carbon radical addition to CC multiple bond. Now come to the third one. This is also addition type of reaction, but it is cyclization. So in cyclization, because it is intramolecular, so that is why it is ultimately cyclization. Mechanism, same type of mechanism you can consider, you can also try it yourself. So in this molecule, as you can see, it is written in, it is drawn in this way so that you can understand how the cyclization is actually occurring. Now ABC, 3 carbons I have marked because radicals can be generated in any of these positions. Now it is not that all these 3 will be generated in equal amount, there will be different percentage. Now this 5-member ring that you are seeing, where A and B, these 2 carbons are connected, and when these 2 are connected, radical will be on C. This is this will give you the major product. Fine. And then if A is connected with C, then the radical will be on B, and if there is no cyclization, directly that when the C-Br bond is broken, you are getting the radical here, which is the third possibility. But finally, the final product, if we consider, after taking proton from, after taking H from Bu3SNH, this is the final product. Now percentage, if we see, this is 81%. That means it is the major product. The 5-member compound, it will be formed in major amount, and these 2 are in lesser amount, 17% the last one, and 2% that is the 6-member ring. So okay. So this is mostly in this case, that is cyclization by intermolecular addition reaction, 5-member rings are mostly generated. Now some more reactions we will see, more examples. So here this, focus on this part. So this carbon bromine bond, if it is cleaved, the radical will be generated here, and this is the multiple bond, it will be connected here, so that you can see the newly generated bond, it is in blue color. Fine. It is not connected at this terminal position. In that case, it will be 6-membered. But as I have said, 5-member ring generation is, the probability is more. One more example we will see. Now this is very interesting because here the radical will be generated first in this position. Obviously, once this CBr bond is broken. Now this will be connecting to this point, and when it is connecting to this point, the next radical will be generated here. Okay, and finally it will attack here, that is this position. So we are getting another 5-member ring. So the two newly generated carbon-carbon bond, you can see it in the product side, it is in blue color. Okay, and finally this CC bond, that will also be broken, and there will be addition of this hydrogen, which is coming in the final step from Bu3SNH. So these are the 3 reactions under, that is, addition. But in all these cases, see, here we have a radical which is attacking some spin paired molecule. We are getting a newly generated spin paired molecule and also a radical. So this you will find in all these examples. But all these reactions are under addition type of reactions. Next video we will see that substitution reaction is also possible with this type of fate of this type of fate of radicals. Fine. Okay, we have some points here. Here all the reactions that you have seen, if you consider the summary, basically it is a trapping of carbon radical intramolecularly and particularly with a CC double bond. That is the most common compared to triple bond. And this type of trapping of carbon radical intramolecularly, it is very common in organic synthesis. It is extensively used in organic synthesis when we want to make some cyclic compound, like especially 5-member ring. And this valuable strategy has found many important applications for preparation of carbocyclic, not just carbocyclic, also heterocyclic natural products. So from synthetic point of view, application point of view, this is very important. That is the last one. Fine. So that's all for this video. If you find it helpful, please like, share, subscribe. I will meet you in the next video.